Section. Introduction. We're going to discuss a new approach in the field of computer vision and image generation, which has been dominated by the use of transformers. These models have been successful in natural language processing and have recently gained popularity in computer vision. The standard approach involves breaking down images into sequences of patches, embedding these patches linearly, and then feeding the resulting sequence of features into a transformer encoder. This method has proven to be effective for various tasks such as image classification, detection, and segmentation. However, this approach has its limitations when it comes to image generation. The reason is that generative transformers require discrete tokens from a fixed vocabulary, which is not suitable for mapping an image to a sequence of feature vectors. To overcome this, recent works have used a two-stage approach. First, they use a vector-quantized variational autoencoder, VQVAE, to map images to a sequence of discrete tokens. Then, they use a transformer decoder to model the distribution of these discrete tokens. This two-stage approach has its own set of challenges. For instance, the size of the vocabulary in VQVAE determines how much information can be stored in the latent code sequence. A small vocabulary can simplify the latent modeling but also makes the latent code less informative. This can affect the control of the low-level details in image generation and the quality of the tokens for dense prediction or low-level discriminative tasks. Increasing the vocabulary size can lead to low vocabulary utilization and consume a lot of memory, especially in multimodal contexts. To address these issues, we propose a new approach that modifies the decoder-only transformers. We suggest a generative transformer decoder that operates on sequences of real-valued vectors, which we call a Generative Infinite Vocabulary Transformer, GIVT. This model does not require discrete tokens or fixed vocabularies. Instead, it uses a sequence of real-valued vectors and predicts the parameters of a continuous distribution over these vectors. We train this model in the same way as standard transformer decoders, with a causal attention mask and teacher forcing. While GIVT can be applied to any sequence of feature vectors, it can be challenging to model sequences that are too long or follow a complex distribution. Therefore, we first learn a lower dimensional latent space with a Gaussian prior VAE, and then model it with GIVT. We also use various inference schemes from the sequence modeling literature. Our findings show that GIVT matches or outperforms the standard discrete token transformer decoder on both image generation and dense prediction tasks. We also derive variants of standard sampling techniques for the continuous case and demonstrate their effectiveness. We study the relationship between the degree of VAE latent space regularization and the resulting properties of GIVT. We highlight that the training of the VAE and GIVT only relies on standard techniques from the deep learning toolbox. In the next section, we will discuss related work in the field, including the use of VQVAE for visual data tokenization, discretized mixtures of distributions, VAEs with learned priors, and time series modeling with transformers. Section Summary. Transformers have become popular in computer vision by splitting images into patches and feeding them to a transformer encoder, but this approach is not suitable for transformer-based image generation. To address this, a two-stage approach using a vector-quantized variational autoencoder, VQVAE, to map images to discrete tokens and a transformer decoder to model the tokens was proposed. However, this approach has limitations, so a modification called Generative Infinite Vocabulary Transformer, GIVT, was introduced, which operates on sequences of real-valued vectors instead of discrete tokens, achieving comparable or better performance in image generation and dense prediction tasks. Section. Generative Infinite Vocabulary Transformers. Let's delve into the concept of Generative Infinite Vocabulary Transformers, GIVT. Our approach is somewhat similar to recent studies that train decoder-only transformer models on the discrete codes of vector-quantized variational autoencoders, VQVAEs. However, our method differs in a significant way. We don't use quantization, meaning we don't use VQ. Let's break down the components of our method. First, we train a continuous beta VAE, a type of variational autoencoder, with a Gaussian encoder and prior. This is a process that was originally proposed by Kingma and Welling. Given an input image, the encoder predicts the mean and variance of a multivariate normal distribution with a diagonal covariance matrix. It then samples a representation from this distribution using a technique known as the reparameterization trick. The VAE decoder then maps this latent sequence back to an image. Since we use a Gaussian encoder distribution, the Kullback-Leibler (KL) divergence term in the evidence lower bound (ELBO) can be computed in a closed form. For the reconstruction term in the ELBO, we use a combination of mean squared error (MSE), perceptual loss, and generative adversarial network (GAN) loss for image generation. For dense prediction tasks, we use categorical cross-entropy. Our encoder spatially downsamples the input image, resulting in a latent representation with spatial dimensions and feature dimension. The hyperparameter beta, which multiplies the KL term, controls how strongly the latent representation is regularized. This regularization is important for modeling the resulting latent distribution well. Next, we train a GIVT to predict the latent distribution. We flatten the latent representation into a sequence of real-valued vectors, which we refer to as soft tokens. This is different from the standard VQ-VAE-based setup, where the latent transformer decoder models a sequence of integers denoting codebook indices. We make two small changes to the standard transformer decoder-only architecture. First, we replace the embedding lookup tables at the input with a single linear layer to project from the feature dimension to the transformer hidden dimension. Second, at the output, we don't predict a categorical distribution. Instead, we let the transformer predict the parameters of a continuous distribution. We model each of the entries with a Gaussian mixture model, GMM. The GIVT model then predicts parameters that we interpret as scalar GMMs. We found it beneficial to normalize the mixture probabilities with a softmax activation, and the variance parameters with soft plus. We use the standard cross-entropy loss on the distribution predicted by GIVT. We train two types of GIVT models. In the first type, GIVT causal, the latent representation is flattened into a sequence line by line, and the GIVT predicts every vector in the sequence conditioned on all previous vectors. This is also known as teacher forcing. For class conditional image generation, we prepend a class vector to the input sequence. In the second type, GIVT mask GIT, we mask the input randomly during training and then gradually uncover the masked tokens during inference. Since we have infinitely many tokens, there is no obvious choice to define a special mask token. Instead, given the latent representation and a mask indicating for every spatial location whether it is masked, we first replace the locations in the latent representation corresponding to the mask with zeros. We then embed it with a single dense layer. Additionally, we concatenate one of two learned special vectors in the feature dimension, a mask vector for masked locations, and an unmasked vector otherwise. Section summary. The method described in this section is similar to training decoder-only transformer models on the discrete codes of VQ-VAEs, but with the key difference of not quantizing or using VQ. The authors first train a continuous beta VAE with a Gaussian encoder and prior, where the encoder predicts the mean and variance of a multivariate normal distribution and samples a representation from it. They then train a GIVT to predict the latent distribution or class conditional latent distribution by flattening the representation into a sequence of real-valued vectors and using a transformer to predict the parameters of a continuous distribution. Section. Inference. We'll now discuss how we use a variational autoencoder, VAE, and Gaussian inverse variance transformer, GIVT, that we've trained. We can use GIVT in two ways, causally or in the same way as mask GIT. We'll also look at different methods of inference that have been developed for discrete transformers and how we can apply them to continuous models. These methods include temperature sampling, nucleum sampling, and beam search. In text sequence models and VQ-GAN-based methods, it's common to adjust the sampling algorithm. We start with temperature sampling, which for discrete models, modifies the softmax temperature of the predicted categorical distributions at each decoding step. For GIVT, we scale the standard deviation of the predicted Gaussian distributions instead, a strategy we call variance scaling. As we'll see later, this small change can significantly improve the quality of the samples. Nucleus sampling suggests gathering the largest logits so that their cumulative probability after normalization exceeds a certain threshold, like 0.8, and then sampling from this reduced support distribution. In GIVT, we can approximate this by truncating the predicted distributions per dimension, which results in choosing a higher density support. We found that this has a similar effect to variance scaling, so we didn't pursue this strategy further. We also use beam search, which works the same way for GIVT as it does for discrete transformer decoders. For each sample, we maintain a certain number of beams, and at each step, we sample a number of candidates for each beam. We call these fans. We then calculate the cumulative log probability for all beams and fans up to the current sampling step, and select the beams with the highest cumulative log probability. However, there's no equivalent concept for top K sampling in GIVT because it predicts continuous distributions. In the diffusion literature, a method called classifier-free guidance, CFG, has been used successfully. This involves training conditional diffusion models with an additional null class to learn the unconditional data distribution. Then, during inference, the conditional log density is shifted away from the unconditional one. Given a guidance weight, the updated score estimate is obtained by a certain formula. We've derived a variant of CFG for our GIVT, which we call density-based CFG, dBCFG, since we directly predict a density. We train GIVT with an additional null class, and during inference, we run GIVT twice at every step, once conditional on the actual label and once conditional on the null class. To implement classifier-free guidance, we then have to sample from an unnormalized version of the density derived from the two GIVT predictions. We use rejection sampling, which requires an unnormalized density, a good proposal distribution that is close to the true target distribution, and a scaling factor to bound the likelihood between the proposal and the unnormalized target density. In our setup, all the distributions we mix are Gaussian. We find that the unconditional distributions tend to have larger variance than the conditional ones. So, it makes sense to pick sample proposals from a distribution with parameters predicted by GIVT when given the actual label. We find that drawing 1,000 samples is enough to find at least one valid sample 99.9% of the time. For the remaining less than 0.1%, we fall back to sampling from the distribution with parameters predicted by GIVT when given the actual label. The overhead of dBCFG is small. It requires 2 forward passes per inference step, instead of 1 to predict the conditional and unconditional distribution. We then draw 1,000 samples from those in parallel on an accelerator, which is very fast. We provide Python code for this in the appendix. Section summary. During inference, we explore different sampling algorithms for discrete transformers and derive their continuous counterparts for GIVT. We investigate temperature sampling, nucleus sampling, and beam search, while also introducing a density-based classifier-free guidance, dBCFG, approach called dBCFG for GIVT. dBCFG involves training GIVT with an additional null class and sampling from an unnormalized version of the density derived from 2 GIVT predictions using rejection sampling. Section. Experiments. We've conducted a series of experiments to demonstrate the versatility of our generative image vision transformer, GIVT. We've used it for image generation tasks, using ImageNet as our dataset. We've experimented with both class conditional generation, where we instruct our GIV to generate images based on specific class labels, and unconditional generation, where we let it generate images freely. We've also used a variational autoencoder, VAE, setup similar to the one used in MaskGIT. This setup uses a VAE architecture made up of res blocks, with a total of 53.5 million parameters. We've removed the vector quantization, VQ, layer and replaced it with a linear layer that predicts the mean and standard deviation. We've used the same weights for reconstruction, perceptual, and GOM loss, as well as the same optimizer parameters. We've only varied the latent dimension and the weight of the KL term. For our GIVT, we followed the original transformer decoder architecture but made a few modifications. We've removed biases from attention layers, MLP blocks, and layer norms, and replaced ReLU with JLU. We've also removed the attention mask during training and fed masked inputs instead of shifted ones. We've used the BERT large configuration unless stated otherwise. We've trained our GIVT models to predict a single Gaussian distribution by default, but we've also experimented with predicting a mixture of 4 distributions per dimension, and predicting a multivariate Gaussian modeling the full covariance matrix of the tokens. For the conditional generation experiments, we've used a learned embedding which we prepend to the embedded token sequence. To train GIVT, we've used the eta factor optimizer with a cosine schedule, set the learning rate and weight decay to 0.001 and 0.0001 respectively, the optimizer's second momentum term to 0.95, the dropout probability to 0.2 for GIVT causal and 0.4 for GIVT mask GIT, and the batch size to 8,192. We've used the same data augmentation as during VAE training, and sampled from the VAE encoder distribution for every batch. We've implemented GIVT in JAX and used the JAX version of TensorFlow probability to implement the predicted distributions and compute the log probabilities. We've trained GIVT casual and GIVT masked GIT models for 256 by 256 ImageNet, and GIVT masked GIT additionally on 512 by 512. To better understand the relationship between the feature dimension, the strength of the KL regularization, the reconstruction quality of the VAE, and the sampling quality of the GIVT, we've trained VAEs with latent dimensions of 4, 8, 16, 32 and KL regularization weights of 0.000025, 0.00005, 0.0001, 0.0002 using the VAE training setup described earlier. For each of these VAEs, we've trained a causal GIVT with the smaller BERT-based dimensions. For evaluation, we've reported the FID when reconstructing the 50K ImageNet validation images for the VAEs. For our GIVT variants and baselines, we've reported the sampling FID when sampling a balanced set of 50K images covering all ImageNet classes. We've also reported precision and recall. Finally, we've evaluated the representation learning capabilities by training a linear classifier on an average pooled intermediate representation of unconditional GIVT causal. Section Summary. In this section, the authors conduct experiments to demonstrate the versatility of their GIVT model. They explore tasks such as image generation using ImageNet, VAE setup, and different variations of GIVT models. They also discuss the training process, including optimizer parameters, data augmentation, and batch size. Additionally, they evaluate the performance of their models using metrics such as reconstruction FID, sampling FID, precision, recall, and representation learning capabilities. Section: Panoptic segmentation and depth estimation. We're building on the UVIM framework, which is used to compress the label space of computer vision tasks. This framework uses a VQ-VAE and an encoder-decoder transformer that takes an RGB image as input and predicts the associated dense labels as discrete codes in the VQ-VAE latent space. In our work, we replace the VQ-VAE with a beta-VAE and use a GIVT encoder-decoder to model the continuous latent code. For the VAE, we use the same transformer-based autoencoder architecture and cross-entropy loss as in previous works. We set the dimensionality to 16 and the KL weight to 0.00025 for panoptic segmentation and 0.0002 for depth estimation. To build an encoder-decoder GIVT model, we use the causal variant described for ImageNet generation and insert a cross-attention layer after each self-attention layer. We use the ImageNet 21K pre-trained VIT-L16 as the encoder, set the image resolution to 512px, and adopt the preprocessing and optimization hyperparameters from previous works. We found that increasing the weight of the KL term in the VAE leads to worse reconstruction but better sampling quality. This is because the VAE can store less information in the latent, shifting more of the modeling effort to the VAE decoder. However, the VAE latent sequence more closely follows the Gaussian prior, making it easier for the GIVT to model. We chose a beta value of 0.0005 for the VAE used in our main models, which obtains a reconstruction FID of 3.66. We also found that the latent dimension has a small impact on reconstruction and sampling FID. In terms of image generation, our GIVT causal models outperform the quantization-based VQ-GAN in terms of FID, even though VQ-GAN has more than 4 times the model parameters. We also found that temperature scaling improves the results for causal models, but not for our GIVT masked GIT models. For larger images, our GIVT masked GIT scales to this resolution and obtains an FID of 5.81. The model produces high-fidelity, coherent samples. In terms of representation learning, GIVT causal matches VIM plus VIT, which has more than 2 times the model parameters and 4 times the sequence length. GIVT causal is only outperformed by MAGE, whose latent encoder-decoder architecture is better suited for representation learning than decoder-only models. Section Summary. In this section, the authors propose a modification to the UVIM framework by replacing the VQ-VAE with a beta-VAE and using a GIVT encoder-decoder for continuous latent code modeling. They experimentally show the impact of varying the weight beta of the KL term on the reconstruction and sampling FID, and they find that increasing beta leads to worse reconstruction FID but improved sampling FID for GIVT models. They also compare the sampling FID of their GIVT models with other generative models and show that their models outperform the quantization-based VQ-GAN. Section: Panoptic segmentation and depth estimation. We're going to discuss the comparison of two models, one based on GIVT, grouped instance vector transformer, and the other on VQ-VAE, vector quantized variational autoencoder. Both of these models lack context in their encoder-decoder setup. We tested these models on two datasets, COCO Panoptic 2017 and NYU Depth V2. We used two metrics to evaluate their performance. The first one is the Panoptic Quality (PQ) metric, which measures the effectiveness of panoptic segmentation. The second one is the root mean square error (RMSE), which is used to assess the accuracy of depth estimation. Our findings show that the GIVT-based model slightly outperforms the VQ-VAE-based model in panoptic segmentation. However, when it comes to depth estimation, the GIVT-based model falls a bit short compared to the VQ-VAE-based model. We've also included some visual results in the appendix for a more detailed comparison.